Okay, let me start by doing a very quick introduction. It is my pleasure to have two outstanding speakers that are going to talk to us about different aspects of quantum computing. As I said, the first speaker is Kirk Brosnicker. He's a HP Fellow and Vice President and currently the Hewlett-Packard Labs Chief Architect. He joined exactly 33 years ago to the day, HP, right out of Santa Clara University, and has been with Labs, the research organization, since 2014. He coordinates the various engagement with the quantum ecosystem and community across labs, the business groups, the government affairs, and our venture fund called Pathfinder. He will talk to us about extraordinary claims require extraordinary engineering, which is referring to some of the quantum development. So we're really looking forward to hear what he has to say. Our second speaker is Greg Byrd. He is a professor and associate department head at the EC department at North Carolina State. And he's also currently the general chair of the IEEE Quantum Week conference and co-authored recently a textbook on principles of superconducting quantum computers. So it's pretty much an authority in the field. He's also worked on other fields like parallel computing, graph processing, and memory systems. And he holds a PhD in EE from Stanford. And he will talk to us about sort of the computer engineer perspective on quantum computing, which is sort of interesting as well. So this said, I'm going to turn my video off, save a few bytes of bandwidth, and I'm going to turn the microphone to Kirk for his first session.
Thank you, Paolo. And I will also start to share some pictures. And so I will also turn off my video, save my GPU, and maybe contribute a couple more watts back to the California power grid so that we can keep the pictures going. All right. So I'll share this. There we go. So thanks, Paolo, again for the introduction, and thanks, Greg, for participating. I guess if Greg, if you're going to be giving give the computer engineers perspective, maybe mine is a little bit more of the systems engineer perspective, and again, a little bit more background on me. So as Paolo said, I started the day after Labor Day in 1999 at HP. Made my way up through all of our server business units. So back in the day, just before I came to Labs, if it had an HP logo on it, and then computed, everything above the laptop was my technical remit. And I came to Labs in 2014, not to make a late career pivot from engineering and into research, but to try and fill a uncomfortable but very important spot. When I was thinking about and living the life of the chief technologist of our server global business unit, I was looking out 1 to maybe 3 years for our mission critical and our fault tolerant systems that demanded that kind of roadmap, because our customers needed to understand and predict were we going to remain in the business, because it would take that long for them to unwind a position that they are in. And so that's what they wanted, more about understanding how we saw the market and how we saw the technologies evolving, rather than any one particular feature. Now, at the same time, I could come down to Palo Alto and talk to the Labs team, and they were looking at 5, 10, 15, or even 20 years. And in fact, back 10 years ago, we had the team under our senior fellow, Ray Beausoleil, who was looking at diamond nitrogen vacancies on diamond as a potential quantum computing qubit modality. Now, that team actually decided to stop that pursuit when they did not see that direction of scaling, of integration, of really applicability to end customer problems. But I think overall, one of the things that was so challenging, and one of the reasons I came to the Labs, is if I think back to when I started, back into the 90s, when I was designing my first PA risk system board, the integrated PCB that was the heart of one of our entry-level PA risk systems. First off, it was a smorgasbord. It was our brand new CMOS, HP CMOS process, PA risk processor. So designing the process, designing the architecture, the way we soldered those components down to the board, and above that, operating system, libraries, middleware. In the end, it displayed on an HP terminal. It was saved off to an HP disk drive or printed off on an HP printer. A vertically integrated solution, which meant that technologies and technologists were very permeable, from our labs teams who were developing both process and technology and services, and it was very permeable to our business groups that I was in, or to our service organization, or to our partners. Now, fast forward to when I came to labs in 2014, and with the lab teams looking out 5, 10, 15 years, that far, so vital, far ahead perspective, and I was looking at 1 or 2 or 3 years, and we had now what is amounted to a global supply chain, where we had to understand not only the technologies that we could bring to bear, but how that entire design community was going to come together. I think that was really what we wanted to understand, how we could continue to get the best out of our research and advanced development teams, how we could harness the engineering and delivery capabilities of a global company, and fill that intermediate gap, fill that uncomfortable middle space beyond, when something was ready to move beyond the research and into industrialization, into scale, into integration, into real customer value delivering systems, but it wasn't necessarily completely done. So how do we actually get a design community understanding, how do we get a regulatory governance model understanding, how do we get that investment teams understanding where these technologies are in their maturity, so that all of us can make those well-reasoned investments of our time and our talent and our careers, and those always scarce investment dollars, whether that's public investment or that is private capital. So understanding how we begin to do that, that was really why I came to the labs, was to sit in that uncomfortable middle space, pull technologists and researchers from the lab team a little bit closer to the business, pull some of the business teams away from the kind of evolutionary development that they were so used to, that constant improvement, and start to understand what if they began to defy a conventional way of approaching things, and what would it mean, and then start to describe some of that at scale. And I think that's what I'll be walking you through today. As Paolo said, I've picked up the opportunity to coordinate across Hewlett-Packard Enterprise, and this is because this quantum is not just a technology problem. It is a technology problem, absolutely. It is a series of technology problems, but it's also policy challenges. How do we make those investments? When and where? That's the constant refrain I keep getting asked from our customers and our partners. When is quantum computing going to be important for me to understand, whether it's a competitive threat or a competitive advantage? And also where in the computational landscape should I be looking to apply these technologies? And especially as we are seeing now, computational workloads turning into really edge to cloud to exascale workflows. The way that we compute, what we compute, where we do this computing, it's all changing, and those applications are becoming much richer. And so understanding how all these things together, that's sort of my opportunity at HPE and working with labs. And again, working with our global affairs team, working with our Pathfinder Venture Fund to begin to do that, and then working really inside of the company, especially given our increasing capabilities, first with the acquisition of SGI and then of Cray, to really lead the world in delivery of the most performant traditional high-performance classical computing systems, as we look forward to what is that going to be? What is that integration? What is that heterogeneous computing environment? How does quantum factor in next to all of these other emerging technologies? So I wanted to start with a little bit, and hope we get my slides advanced. It seems like this is a fantastic week to have this discussion, because I don't know if you've been getting people sending you a lot of headlines and clippings, but over the last week, and really it's over the last several years, either everyone is predicting a bubble is about to burst, or we're just pumping it up as fast as possible. Back in 2018, in the IEEE spectrum, the case against quantum computing. Back in May of this year, IonQ, and this was a rather spectacular almost 200-page assessment from a short-selling venture firm, and really trying to poke holes in IonQ. And full disclosure, IonQ is one of those companies that our Pathfinder venture arm has invested in, because, and that was actually in consultation with the Hewlett-Packard Labs team. So it was really interesting to see, this kind of interesting assessment, and especially when it's 200 pages and written in Reddit r/manifesto font. The quantum bundle, this was just this last week, Nikita Goryanov at Oxford, really trying to ask the same question. What should we make of the current state of quantum computation, given the funding, given the investment? And again, I'll put in here, not just the investment of dollars or pounds or euros or yen or renminbi, but also the investment of time and capacity between our research organizations, our academic institutions, our global research organizations, and industry. And at the same time, then, the very next day, Simon Benjamin it provides that question, are we too skeptical, not skeptical enough? And I guess for me, hopefully being, again, a systems engineer at heart, I'd rather not be too skeptical nor skeptical enough. I'd rather find that middle ground. The old joke, the pessimist says the glass is half empty, the optimist says the glass is half full, and the engineer says the glass is designed twice as big as the average use that we're seeing. So understanding how we begin to separate this out, and I think that's a healthy way for us to do it. And what I'll do with the rest of the talk is go through a little bit of what I've been seeing as I've come into quantum from the systems perspective, from that position of trying to be in that uncomfortable middle space between research and productization, point out where I see some of the challenges, talk a little bit about history, and then where we think, what I'm seeing as part of what we want to bring into the conversation, and then we'll toss it over to Greg and see how far away his view from the computer engineer is from what I'm seeing as that systems engineer. So this is an example of, and I purposely obfuscated the vendor here, but this is a roadmap from one of the quantum hardware vendors. And oh shoot, I made an error when I made this slide. At the bottom, it's not supposed to say 2021 all the way across. It's supposed to be every single year from 2021 to 2027. And when you notice is that this is the qubit count, and first thing you got that nice exponential growth. And as a matter of fact, it's a little bit different. It actually is growing kind of flat, and then boom, and you see that little superscript next to what should be about 2025, and then another one at the end. And then down at the bottom, you'll see, and I've seen this as I've talked to the hardware providers really across the industry, they'll all have a similar picture. They're showing internal growth, and then it's punctuated by breakthrough. And that certainly could be the kind of development that we should anticipate in quantum. As a matter of fact, I think that's most likely the situation. Continued improvement, and then bang, you're going to get something. You're going to get a breakthrough. Now, the challenge that we have is that everyone who sees this chart, if they have been paying attention since 1970 on to now, they're thinking about Moore's law. They're thinking about every other year you're going to double the resource. And unfortunately, even with Moore's law, what we tend to see is people thinking about doubling of performance, when really the vertical axis should have been always with Moore's law, the number of transistors per unit area. And in this case, it's qubit. And so that's the first challenge we have when we talk about these roadmaps, is that they end up being shown linearly in time across the horizontal axis every year, but they're punctuated by these breakthroughs. And that's the problem with breakthroughs, is that they're a lot harder to predict, even with a robust road mapping environment. They're harder to predict than you'll have when you are making that incremental improvement. The other challenge with all these graphs is the vertical axis. The vertical axis is qubits, and unfortunately, again, why we're taking the analogy with Moore's law, and what we see there is that people will load up with transistor count, and even if it really is the real transistor density per unit area, and we look at the improvement over time, there's just so much history there, because almost all of us can take that kind of a number and then relate it, because we've had the experience of relating that capacity per unit area with performance or with any of the financial benefits that we derive from running these applications. So all of it is something that we could all understand. And unfortunately, with qubits, it simply is not enough. We really need to know so much more. And there are certainly all of those dueling measures of efficiency and efficacy. Oh, it's about quantum volume. Oh, it's about the number of circuits per second. Oh, it's about coherence time. And so unfortunately, the vertical axis that we have, that is what people are familiar with in both the technology community as well as the investment community, is this monodimensional number, the number of qubits inside of the quantum system, and that is simply not sufficient. So that's why I put at the top, I think it was one of the technical leads at D-Wave, called this, Rose's law, after their founder, one of their founders, and unfortunately, there really isn't that equivalence right now. It's not equivalent in the vertical axis. It's really not equivalent in the horizontal axis yet. I think we can work towards that, and that might be a useful goal. I know in working with some academic researchers, Purdue, Indiana, and Notre Dame are proposing to the National Science Foundation a industry university cooperative research center focused in on quantum technology. And one of the leading assignments that they would like to tackle is to provide some kind of an independent framework, knowing that we really need more dimensions than this vertical axis. We really need to understand how we plot out that horizontal axis, where there's a relationship that people can begin to design and begin to understand. And again, that's as much for us as technologists as it is for the fiduciaries who are making investments or the customers who want to understand. I think the last thing about the challenge we have with this slide, and I've mentioned it once, but I think it's worth reiterating, is it doesn't really talk about what people want to do. And Greg, it'll be interesting when you give your talk. I've wondered many times, if it weren't for Shor's algorithm, if it weren't for the possible defeat of public key cryptography by emerging quantum systems, if it was still just the material science, if it was still what Professor Feynman had suggested, that if we really want to master and understand mechanical systems at the quantum scale, then we would need quantum systems in order to simulate and to map our understanding into that kind of environment. If it was still just, and even that would be spectacular, if it was still just that quantum system, would we see as much energy around this? And so I don't know. It's an interesting debate to have about how we would see this kind of a diagram improved, so that we could all make those better investment decisions. And I think for me, I think we've all seen this posted, pinned up to cube walls or posted up on laboratory bulletin boards, that then a miracle occurs. It's not really an option. We really need to understand so much more about the ways and the mechanisms, the science and the engineering necessary if these systems are to continue to scale. If we really are going to be able to hit some of those points, is not just about the quantum system, not just about the harnessing, creating essentially, to me, what seems like, let me create a tiny pocket universe completely separated away from the rest of the universe. I will create a quantum system in there. I will be the sole and only manipulator of this system. I will master its behavior. I will control it. And in return, it will give to me, incredible computational power. And then for me, the real question is, okay, well, let's assume that you actually are able to harness some of these qubits in that way. The counts continue up. What are those ramifications? It's one thing to learn how to make a little ammonia in your high school chemistry class. It's another thing to plan and to industrialize a Haber-Bosch process that swallows reactants by the train car load, and then be able to deliver all of that economic benefit at industrialized scale. So I think that's where I think a conversation would be beneficial, and maybe even a little bit of history. And for me, it's fascinating to think of, and so sometimes you hear again with the question of Moore's law or the analogies drawn to semiconductors. And I think it's instructive to remember something about transistorization, and then following it up with the rise of integrated circuits, because if you think back to 1947 and Bell Labs and this very first transistor, now here we are. All of us expect to go and buy consumer devices where there are literally billions of these devices. We expect to pay, almost, when you divide it by the cost, billions, hundreds of dollars for billions of devices. I expect them to run forever for very little power. I expect them to do everything I want. That's a fantastic leap forward in only 75 years. But it's also interesting to look at that first consumer 9-volt radio was only 10 years after the very first contact device, the first commercial transistor computer from IBM, again, 11 years later. So there was a rapid adoption of the transistor and then the integrated circuit, enabled by academic and industrial research working together, and it was very fast. But part of the reason it was so fast is this was following up 40 years worth of vacuum tube design, and modulo the fact that transistors are low impedance and vacuum tubes are very high impedance. That ability of the swap, the space, size, weight, and power benefits of the transistor, plus the engineering to reduce the cost, enabled this sort of quick and easy jump into an established design, not just an established individual designs, but established design community. If you ever go to the Computer History Archive Project YouTube channel, go and look at some of the films about introducing transistor technology to the vacuum tube engineering community. And they were able to leap into this with relatively straightforward. And then when the industry came together to make it affordable, not just a tube replacement, but they were then able to extend. And then when you think of the design tools that were then brought to bear, we can really see how we're able to do that. And I think for me, it's important that when I see what we can do with quantum systems today, I think we're a lot closer to RAMAC, and that's what these are. These are pictures from the RAMAC operator's manual, back when computation was these really individual elements that could accelerate what at the time was a physical mechanical process, a manual process, and you plug them together literally with plug boards, created these flows. The flows today that we run through in our debuggers used to be the flows of patch cables. And I think right now, this is kind of where we are in reality. But when we look at the material, when we see the aspirations of the community, when we see the work of the theoretical quantum computational science, it seems like they're so far past this, and they're not even at that EDVAC, that von Neumann equivalent architecture. We're much closer to this in reality, and I think that's part of the challenge we have is understanding what advantage could we have right now, and then how do we begin to roadmap that out. So I think for me, it's, again, learning from history, irds.ieee.org typo again on my slide, apologies, .org, this is that, again, looking beyond just that individual transistor and how it was adopted to the scaling. I think I was reading today that we as a species have manufactured something like 10 to the 22 MOSFET transistors. Our species really could be, Homo MOSFET, because that's the number one thing that we have produced by scale and economic benefit as a species. And one thing that happened is that didn't happen certainly overnight, but it also happened because global design, industrial, academic, and public and private investment met first as the National Technology Roadmap, the International Technology Roadmap for Semiconductors, and now as the International Roadmap for Devices and Systems. And through these different eras, the first era that Gordon Moore would have recognized, 75 to 2002, that he described, and we kept going. And then, equivalent scaling 2003 to 2024. So we're just about done with the second era. That came about, when some of those features, because of the geometric scaling, were about to scale to zero. We did get, what amounts to what we would call a breakthrough, except it wasn't. It was a concerted effort to analyze and drive to solution a series of technical challenges that the community came together, academic, industrial, public, and private, came together, elucidated the issues, and then systematically worked them out, and then did the roadmap. And here we are now, about to enter that third 3D power scaling. At this point, a little bit more of an if than a when. We are there for memories. When and if we'll get there in terms of general 3D scaling of logic. I think that's an interesting area that we'll continue to research. But certainly at the 2.5D, the chiplet, all these things coming together. Frankly, that last page of Gordon Moore's original paper, I think, presages the area that we find ourselves in now. But we're also, again, we're seeing that global community use a road mapping methodology, systematically evaluate the challenges in front of us, and then go through them. But all this time, we were deriving value. And I think part of the challenge that I, as a system engineer, see as I enter in some of the discussions with the quantum community is they seem to be aiming for the leapfrog, aiming for the home run, rather than all of those singles that we were doing for decades here in the semiconductor community. So I've been having these conversations, and along with me, Ray Bosley, our senior fellow, leading our large-scale integrated photonics. And one of the ways that he's been looking at this is we seem to find ourselves right now with the noisy intermediate scale quantum hardware building up the teams that are trying to work on the low-level qubits, and it's all about trying to figure out how can I improve these individual qubits, no matter whatever my modality is. There's more than a half a dozen competing computational modalities, whether it's superconducting, whether it's ion trap, photonic, Rydberg atom, neutral atom. There are just so many ways. I think there's still people who are doing the diamond nitrogen vacancies that Ray and his team did their work on a decade ago. It doesn't seem like there's a clear winner. It doesn't seem like there really is one that has all of the advantages and no disadvantages. And so I think we'll continue to see all of these, but everyone's pushing on their own individually, and they're building up, and then they're, in some degree, I almost use the word hope, but I think they are betting on, maybe that's the better term, they are betting on the ability to continue to improve these so that they can achieve a fault-tolerant quantum error correction mechanism. And the estimates are all over the map, depending on the modalities, is that 1 to 10, 1 to 100, 1 to 10,000, actual quantum devices to this logical quantum device that we all yearn for, and then to get through the algorithms. And I get one of the things that Ray has been trying to understand is, can we take a page from history? Can we look back to the way in which we adapted and adopted these technologies in part, and then as part of a greater whole? So work, instead of working from the qubits up and hoping that you will project forward and end up with a sufficient set of necessary and sufficient set of capabilities in the qubits, can we work the other side, work it from the other end? Can we work from the applications, the algorithms, down to the actual qubits that we have at any point in time, work from the architectures, work down through the compilers, work down through the correction code, work down through the gates, work down to those lowest level qubits that we actually have, and then understand how we pull them together. So I think for me is beginning to understand and having the conversation about how we're approaching this as a global community, I think could be a healthy mechanism, could be a way that we bring in some of that, more of that learning, more of that understanding, and more as a global community. And I think that's where, you know, conversations like the one we're having tonight, hosted by the IEEE, is an excellent way for us to convene and understand how we pull all of those things together. So again, I said I made the claim of being a systems engineer, trying to understand how all the pieces come together. And for me, I think of three levels that we really need to have the conversation about. The first is the physical, and of course, I will make the not very bold assertion that I think that there isn't going to be one modality that is going to leap up above. You know, again, when I was starting here at HP back in the early 90s, designing those first systems, my first systems, yeah, we had a CMOS processor, but I still had TTL, I still had ECL, I still had individual transistors still doing elements on that circuit board. So even back then, there was not that one winner, and I think that's what we should expect. And so each of the individual modalities, having that conversation about what does it take to continue to scale this physical modality, understanding how it will make then demands on the physical plant. You know, I've had conversations as high performance computing customers have asked us, you know, how much space should I reserve on my next generation supercomputing floor? Do I need to have a helium supplier? Where am I going to, you know, provide the power cooling? Do you have an idea? Can we begin to have that conversation about, if I need to be able to do, and the challenge is that they're talking about high level workflows. If I need to be able to execute one of the new NIST post quantum cryptography standards, what does it need? Or if I need to execute a new physical chemistry application, what is it going to take for me to prepare? So I think having those conversations about those physical systems and bringing more of that system design expertise that I think, you know, I see our supercomputing team, our Cray and HPE Cray team do, as they've just done so successfully in integrating at the exascale computing environment. And that wasn't just, you know, designed for one processor. It was really designed for a heterogeneous environment at every one of these levels, but especially at the physical level. Are we ready to have that conversation? The next one is that cyber physical level, understanding. You know, so often, you know, I'll be reading articles about a particular quantum vendor, and they'll talk about the potential of a qubit. Oh, it can, you know, and they'll try and draw analogies to how we would represent the state of the qubit in conventional classical systems, and then somehow equate that into a storage capacity or one of these elements, and oh, here's 50 qubits, it's equivalent of 50 petabits of information. It's like, yeah, but you know, we're not really designing to pump in 50 petabits of information in order to get 50 classical bits of analysis out. So what does it actually mean to integrate these kinds of computational accelerators at every point in the scale? And have we actually designed the cyber physical system, whether it's the cyber physical system that is controlling, that turns, that actually is exercising your particular modality, whether you need, you know, precise laser pulses, whether you need RF energy, whether you need electromagnetic control. How do we do that lowest level control? And then how does this begin to build up into applications? And finally, is that last piece, is productivity. How do we co-design and engineer at the productivity level, understanding how we take today's applications and begin to pull in quantum acceleration as advantage? And then is there something else that needs to happen in terms of the overall structure of not just quantum, but all of the emerging heterogeneous computational accelerators? And is it possible that we could begin to treat them as a class? And I think one example we'll give, and this is a partnership in Palo, help drive this engagement with Cerberus, the wafer scale AI accelerator. And if you haven't availed yourself of some of the information and the physical engineering that was entirely Cerberus, it is fascinating engineering. But where we began the partnership along with Pittsburgh Supercomputing is, okay, here is this immensely capable engine. How do we begin to plumb it? How do we physically, cyber physically, productivity, how do we begin to plumb this accelerator so that we can actually begin to take advantage? Because that raw capacity, that raw ability to digest that much raw information and then make inferences and pump it through, it doesn't matter how efficient we have in terms of computation per cubic centimeter, per watt, per gram, if we can't keep it fed. And I think for me, that's the question I keep asking as I talk to some of the hardware and integration teams in quantum. Have you imagined success? And can you tell me how many bits per second you need in and out inside of the dilution refrigerator or inside of the vacuum chamber? Can you tell me what is necessary at that next click up in terms of the surrounding? How do I encapsulate your accelerator? And then finally, how do I begin to make this productive? Where is the equivalent of, the Jupyter notebook that will allow someone who just wants to understand graph analytics, who just wants to understand material science, who just wants to understand how to optimize a billion constraints? How do we give them access to this and then break it down into all these elements? So this is one of the lessons that's been provided from our Cray team, is they are used to providing a very bespoke programming environment, and then all of the individual vendors, as well as the open environment. They really wanted to do this over all of their infrastructure, whether this is a 2-socket server or it is that frontier exascale system. And one of the things that they're really exploring along with us at Labs right now, we already have the AI programming environment. Now, we'll give this the GPUs sort of they were already they've sort of had that past. There was that first application specific accelerator, and individual vendors ended up still providing that access. But with the AI frameworks, we have that first example now. Maybe it's possible for us to pump up one level and begin to talk about them as a class, begin to also talk about the quantum programming environment, that quantum ecosystem, that compiler collection as a class, so that underneath, we now have those third-party products, those APUs, those QPUs, and perhaps even some quantum-inspired classical accelerators, understanding how all that comes together and begins to make these environments for productivity something that we can begin to reason over. And I'll just show one more slide and then pass it on to Greg. And I guess this is, again, as I said, I'm in the fascinating position of sitting at Labs and then working across the communities inside of Hewlett-Packard Enterprise, both our policy teams, global policy teams, as well as our venture fund, and then also working externally. And it's not just the team that we've had Labs, the acquisition of both SGI and now especially of Cray has given us access both to customers, partners, and also engineering of that caliber necessary to integrate at the absolute leading global edge of high performance computational systems. And so I get to sit in between this, and part of that is to understand, how do we continue that heterogeneous computing development that we have already embarked on and is really instantiated in that exascale systems that are now coming online, the first at Oak Ridge and others to follow, where the CPUs, the GPUs, the FPGA, all of that zoo of accelerators based on classical CMOS, how we begin to integrate them, how we also bring that quantum computing development in. And I think for me, it's really highlighting that goal, integrating classical and quantum systems, harnessing the diverse accelerators, efficiency, sustainability, runtime, security. And I think what we want to understand how we can provide into that, first is that understanding what is that workflow environment like again, starting, if you want to talk about it outside in from the applications inward, if you want to talk about it as our colleague Ray Bosley has been doing about starting from the application and working towards the technologies as opposed to the technologies and hoping or risking that they will end up being sufficient. So I think there's an element there about the unified workflow environment. We won't be returning at Hewlett Packard Labs to the low-level quantum hardware. There's great partners we're finding all over the globe that are, again, working across all those modalities. But we do think there is a possibility for us to add in our quantum-inspired accelerators. These are non-conventional accelerations. This is not just plain old CMOS and put together in a novel way. It's really trying to understand classical physics being harnessed. So you can think of it as photonic or analog computation. Some of them are aiming at exactly the same, some of the same problems that we anticipate quantum advantages, but we might have a little bit of lead time in those. And so is that possibly a way for us to pull all these things together and begin to understand this unified heterogeneous computing environment sooner, or at least in parallel with a little bit different flavor than we're seeing from the quantum. And the last piece that I think we're looking to understand is understanding that industrialization. So whether that is simulation, emulation, integration of today's hardware as it continues to improve, can we talk about how we'll harness all of the supercomputing power that we're bringing on to bear that traditional supercomputing environment, and then understand how we both utilize traditional supercomputing to advance the state of quantum computation, as well as the other heterogeneous computational systems, and then also integrate it at the same time. So I think that's where we really see, there's an opportunity here to really sort of, I think for me, to take stock, find that balance point between it's a bubble that's waiting to burst and we can't pump it up fast enough. Find that middle ground, find that perhaps uncomfortable middle space that I've been at since I've come to lab, but it's been a very rewarding space to try and bring the lessons from the semiconductor community, from the road mapping expertise, from what has enabled us to continue on with semiconductors as long as we have, and create that really cooperative, pre-competitive environment between academic, industry, public, and private, then go into the no holds barred, competitive, vibrant market that we find ourselves in today. I think there's a lot of lessons, and I think part of what we as an IEEE facilitated community can do is to convene, to join in and have these conversations and try and provide those lessons, try and provide that guidance, and also be open to new and different ways to approach these problems, try and find that balance point. So I will stop there and toss to you, Greg.
Yeah, there's only one question. So what I'll do is I'll wait. I think it makes sense to kind of wait to the end and kind of get them all together. Everybody, if you don't be shy, just put your questions in the chat and I'll kind of collect them and kind of aggregate them. So Greg, to you.
All right, so yeah, very interesting, Kirk. Thank you very much. It's very happy to be here. It's an honor to present to you folks. And sort of my discussion is going to be a different flavor. It's going to be a little more professorial, coming from an academic background. And I guess really my goal is to maybe introduce or reintroduce some of the concepts of quantum computing in a way that's a little more approachable to people with backgrounds like mine and not backgrounds like this, right? So a lot of times you hear about quantum computing, like you think you have to learn all of quantum physics to understand quantum computing. And that's not the case, in my opinion. We're quite comfortable with complexity, but it's more of this kind of complexity. And even this isn't all that complex. It's just a little A to D converter chip. But I want to sort of go through my perspective, and as I was learning about quantum computing, and we'll work our way up to things like algorithms. But what I really want to finish with is discussion of some of the opportunities and the system challenges that those of us in the space are working on to try to get to that system that Kirk has described so eloquently. So we're used to abstraction, right? Computer engineers are very happy saying, I don't really need to know what volt is high and what volt is low. Just, I'll treat it as a 0 or a 1. And so you can kind of take a similar model with qubits and say, well, I'm going to model, my abstraction is that a qubit is something that could be or 0 or a 1, or it could be some linear combination of 0 and 1. And if that's, so we sort of take that as our basis. We don't necessarily worry too much about how they're physically implemented. As Kirk mentioned, there's lots of different modalities and lots of different ways to create and control a qubit. So I want to think about, well, let's suppose we have a qubit. What can we do with it? And what does it mean to have a qubit? And here's where some of the power of the quantum computation comes in. When I have n qubits, then what I can do with these combinations, these linear combinations of the possible states, is that I end up with 2 to the n possible states, and I can be in any linear combination of all of them. Whereas in an n-bit classical bit state, I have n bits. It could be any one of 2 to the n things, but it's still only one thing. So it's not this mixture. So I'm showing a little math here, and I mean the thing is that these amplitudes, what I'm showing here in these little balls, are the magnitude is the gray circle, and then the phase is the angle at which this little blue thing is thing, and this would be a phase of 0 and so on. So these are complex numbers that have magnitude and a phase, and the magnitude squared of all of those has to add up to 1. So you as Kirk mentioned, you got this huge space with just a few qubits. You got all these possible states you could be in. One of the downsides to the quantum computing, as you may know, is that we don't get access to all of that data, right? We don't see the entire state in all of its glory. And so what we can do when we observe this state is that we get one number out. We see one of those states. And the probability of seeing one of those states depends on this magnitude squared, but we only get one of the states. And not only that, it gets a little worse that when we actually measure the state and get that state out, the quantum state collapses to that classical state. And so we don't even get to use that again. We sort of have to create it and then look at it. And if we want to do that again, we have to start from the beginning and create it again. So the key thing from a computer engineer's perspective is, okay, I've got these abstract qubits. I know kind of what they do or what kind of states they can be. How do we create those states? How do we manipulate them? And how do we express our problem in a way that can exploit this? Well, the easiest first way for me to approach this is to think about logic, right? So we think about, I'm very comfortable with classical logic and these gates on the left. The thing about quantum logic is that all of the operations that we perform on the qubits are going to be reversible. So there's certain things that we can't just do the way we normally do, like this AND gate in the middle on the left. It's not reversible. Once I have X, Y, I can't go backwards and tell you what X and Y are. But this version on the bottom is a reversible AND gate because I carry through the X and Y, and so I can get back to this original state if I want to. And the way we talk about that in quantum computing is one of the gates that I'll show you in a bit. It's called a C0 gate or controlled NOT gate. And what this gate does is if this X signal is 1, it flips the Y bit. Well, that's just doing an XOR. And this one has 2 controls on it. And so these are reversible versions of the kind of Boolean logic that we're used to. One of the things that we don't get in quantum logic is the ability to replicate state. We can't, it's called the no cloning theorem. We can't take a arbitrary quantum state. We can if it's a 1 or a 0. If I know it's a 1 or 0, I can copy it. But it's one of these arbitrary states that's a mix. I can't just make a copy of it and use it somewhere else. So that's a limitation that we need to be aware of if we're going. And as you think about what you can express just things that we're used to doing all the time, like assign B to A, you just can't do in a general state. I can add B to A, and that's reversible, because to get back, I can also always subtract B. I can't set something to 0. Well, you can, right? In a quantum machine, you have to be able to initialize things, but it's not reversible, so it's not one of these gates that we talk about. So you have to be really careful about what you can do. So what can we do? We build these things out of these fundamental gates. This is an example of an X gate, which is sort of like a NOT gate. Changes 0 to 1 and 1 to 0. We've got this. How do I create these superposition states, these mixtures? Well, one of the ways is with this Hadamard gate. If I put a qubit that's in state 0 through a Hadamard gate, what comes out is this equal superposition of 0 and 1. So that's pretty handy. That's how I can create those kinds of states. The other thing I can do that doesn't really have any classical analog is I can manipulate the phase of the state. So you can see the S gate rotates the one component of the state by 90 degrees, and Z goes 180 degrees, and so on. And so this is sort of unusual, not something we're used to thinking about in classical computing. Here's that C0 gate that I mentioned. So it's called a control knot. One of the qubits is the control qubit, and depending on the state of that qubit, the other qubit gets flipped or not. Once I have that, then I can build these multi-control things. And once I have these multi-control things, this is called a Toffoli gate, I can create AND gates and NOT gates and OR gates. And so now once I've done all that, I can compute anything that's computable. But I always like to say, if what you're doing is building your quantum computer to do classical computation, you're doing it wrong. It's not what you want to do, but at least gives us as computer engineers a starting point to say, okay, well, now I'm convinced this is a universal computing engine. It can compute anything, but it can compute more than what we're doing here. So I could build an adder, right? I could take these 3 qubits here, and here's my output qubits here, and I use these C0s and Toffoli gates, and I get a sum bit and a carry bit. I can feed this carry bit to another set of qubits, and so on. This is a reversible adder. It can be done on a quantum computer. Okay. Now, so far, what I've been talking about with these gates is what does it do to 0? What does it do to 1? But we know that we can have these superpositions. So what does it mean when I do a gate on a superposition state? So let's see what happens. I have these 3 qubits here, A, B, and C. Let's do this Hadamard gate on B. So now B is a equal superposition of 0 and 1. So if I draw that state in this terms of this 8, this 3 qubit state, I would have magnitude here and here, where B is equal to 0 and B is equal to 1. And now when I do this gate on it, if they're both 1, then it flips. So this one flips, but this one doesn't. So we can see that we're manipulating both of the states through this one gate, because the transformation applies to all of the subcomponent states as we go. And we'll see why that's important in a bit. The other thing that we can do, I'm not going to explain the circuit, but other thing we can do is we can encode logic in the phase of our qubits and not just the magnitude, not just 0s and 1s. So for example, I could create this circuit here that says, let me go back here. It says if this B value is 1 and this A value is less than 3, flip the phase. So take it from a 0 phase to a 180 phase. And we see what happens if I start out with this state here, and then we see that these 3 states have been flipped, 0, 1, and 2. Those are all less than 3. B is equal to 1, right? And so we see that this phase thing has happened. Again, it's not something we're used to dealing with in classical logic, but it's going to be a useful way. Once I have these phases, when I combine things with different phases, sometimes they interfere constructively and sometimes they interfere destructively. And so sometimes things go to 0 and sometimes things get amplified. And that's going to be our key to how we create quantum algorithms. Okay, so just like I have logic gates for 0s and 1s, I have these phase logic gates where I can compute ORs and NORs and XORs and so on with the phase information. So I know I'm breezing through this really fast, but I want to get to the fun stuff. So once we have this superposition, the other thing that you often hear about in terms of quantum computing is entanglement. And what does that mean? What does that mean for us? Well, if I think about one of these logic blocks, so I've got this function called use of f that takes an input x and an input 0, brings x out because I need this to be reversible, and then these qubits up here become whatever the function is I'm doing, so f of x. But this is a very common way to write down something, some tiny building block of an algorithm. So for an example, if my function f of x takes x and adds 3, then if I were to take, let's assume that these lines here are, let's say, 4 qubit states. So I take state 0 and state 4, what I get out is, again, 4, this is x, and this is x plus 3, so I get 7 up here, okay? Pretty simple. But what happens if this is not just 4, but some sort of superposition? So let's suppose that the input is a superposition of 4 and 10. Now this has a 1 over square root of 2 kind of thing on this, but I'm going to leave that out just to be simple. So I got this superposition of 4 and 10. I run it through my plus 3 circuit. I get 4 and 10 on the bottom. You might expect I would get 7, a superposition of 7 and 13 on the top. But that's not exactly right. And I'll tell you why it's not right, and I'll tell you why we don't want it to be this. The problem, well, I'll go ahead and tell you that. The problem with that is if I look at this state and I measure 4, and then I look at this state up here and I measure it, I might get 13. That's not the right answer, right? That's not x and x plus 3. That's x and something else. So this doesn't allow us to get the answers that we're looking for. So what we get instead is we have to think about this output not as 2 different 4 qubit states, but as a single 8 qubit state. And what we get is a superposition of 4 and 7 and 10 and 13. So whatever we measure, we're going to get the corresponding value on the other side. Okay, so I think I'll skip this question. It's really, entanglement is weird, but it's not that hard to understand if you work through it. But I'm gonna skip through it nevertheless and just convince you that it's a good thing to have. And it seems like it'd be really hard to create these things that are entangled, but in fact, it's really easy. You take one of these Hadamard gates and one of these CNOT gates, and we get out this state here. So 0, 0 plus 1, 1, that's an entangled state. How do I know it's entangled? Well, if I measure this qubit as 0, then I already know what the measurement for the qubit on the right is going to be. That's part of what entanglement means, right? The measurements are correlated. Even if those qubits aren't next to each other and they're many miles apart, if we entangled them and then separated them, if I measured a 0 over here, I can tell you that it's going to be a 0 over there. Doesn't matter. That's what was called spooky action at a distance, one of Einstein's favorite famous terms. But mathematically, it's not that hard to grasp, and we can entangle multiple things together. And if I go back to my adder, these gates, this CNOT gate here, if you can imagine I put a Hadamard gate here, well, now this is entangled. These two are entangled. So everywhere I have the CNOT or a Toffoli gate, this entangling happens. And that's what ensures me that when I measure sort of the input, and the output that I measure is going to be consistent with the input that I measured. Okay. So entanglement is a really nice property, really good. Okay. So we've got this entanglement. We've also got this this aspect of when I put 4 and 10 in here, I calculated, in a sense, 4 plus 3 and 10 plus 3 at the same time as part of the same operation. And a lot of quantum purists don't like to think of it. You're not doing a bunch of things at the same time. You're doing something to this state that has multiple components. But we sort of call this quantum parallelism, and it's part of the potential power of these systems. Okay, so I'm going to talk very briefly about algorithms and applications. One of the issues that Kirk brought up, and I agree is a very hard problem to deal with, our access to this quantum state over here. If this inside the quantum box, we're doing things with qubits and superpositions and entanglements and all this, but once we measure it, it comes back as ones and zeros, and all we can put in is ones and zeros. So we've got this data bottleneck here where all the parallelism and power happens over here. So we have to figure out algorithms that make sense for us to be able to create enough, explore enough of this huge state that we can use to accomplish something useful. A lot of algorithms follow this procedure of sort of, okay, we know how to create this equal superposition. We just throw a bunch of Hadamard gates at everything. It's really easy. And then we take steps to manipulate those quantum states. And what we're trying to do with those manipulations is we're trying to increase the magnitude of the state that's going to give us our answer and decrease the magnitude of the qubit states that we don't care about. And if we do that well, then when we measure, we're much more likely to get to see something that solves our problem than to see one of these other just sort of random states that don't. So we're trying to amplify the good things and suppress the bad things. Okay, so one quick example. This is usually expressed as Grover's algorithm, but one component of Grover's algorithm that's sort of generalized is called amplitude amplification. And it shows you where this phase information comes in. So it turns out that if I have this equal superposition where one of these options has the opposite phase, then I can amplify that magnitude of that state by doing this operation a couple of times, to where now it's very common that I will measure this state, if this is the one I wanted, than the other states. So this is what the circuit looks like. This little magic step over here, this called the Grover iteration. And what it does is, let me go back to here. If we do this phase-based logic where I do some calculation and flip the phase of one of the qubit states, and then I do this operation here, the way that looks like is I flip the state here, so this positive value becomes negative. And what that extra piece at the end does is reflects all of these states around this average of the magnitudes. So these positive ones get smaller. They go on the bottom side of that dotted line. And the purple one gets way bigger because if I reflect this around that line, it gets way up there. So this is just a cartoon illustration of how this amplitude amplification works. And so that's just one example of one type of algorithm, but it kind of gives you a sense of where this power comes from. It doesn't come from the fact that we're doing something on all 2 to the n things, but we're able to describe the thing we want in a computational way and then sort of amplify that so we get the answer that we're looking for. Okay, so the last few minutes, I'd like to talk about some of the system challenges, things that computer engineers know and love and can work on. I won't use the Moore's law analogy, but this is an analogy that I borrowed from Rod Van Meter at KO University. He likes to talk about the quantum airliner and what it will take to build a very functional quantum computer. And so he used the analogy of we're sort of where we are, where the Wright brothers were when at the invention of flight. they did a lot of things themselves. Right? They designed the airfoil, they designed the engine, they just made a lot of breakthroughs and a lot of designs on their own. But if we look at an airliner today, we see a lot of specialization. We see a lot of interacting systems. These things are being developed and built in many different countries and coming together as a system. And that's the sort of ecosystem that we're going to need. We're going to need lots of different pieces to be developed and worked and come together in a larger system. So what are these pieces? One of the things I'm sure you've heard of NISQ. NISQ stands for Noisy Intermediate Scale Quantum Computers. It's sort of the machines that we have now in the tens of qubit range. These qubits are considered noisy. They decay over time. They don't hold their state for very long. And so, the longer you can hold the state, the more things you can do to it. And so everybody who's working on the physical side is trying to improve that delay time so that we can do more and more things. Lots of sources of noise, including, noise you get when you actually try to measure it, noise you get when you try to control it. Maybe you didn't quite control it exactly the way you wanted to. You've got interference from other qubits around it, lots of things that come into play for noise. And so if this is the state of where we are, if we're in the NISQ era, what needs to happen to get up to this top right, which is the big goal, the fault-tolerant quantum multi-computer, lots of things have to happen. And as one dimension, the Y dimension in this diagram that, again, I grabbed from Rod, is as the qubits get better and better, higher fidelity, longer coherence times, we can do more and more with those qubits and sort of scale up this way. As we add more physical qubits, we could scale over to the right. And what do we do with that? We see this big jump to the left. Once I have a lot of physical qubits that have a reasonable fidelity, then I can implement error control, error correction. And it takes me back to this land of few qubits, because now I have we're talking about logical qubits instead of physical qubits. But this is one way of sort of the roadmap of where things are going. So what can systems people do? Well, this particular chart is really more about, if you have to understand the physical system that you're doing, how do you control it better? How do you interpret what you get out in a better way? How do you mitigate these errors that you get? So that's one whole area of research. Not quite so much on the computer engineering side. There's quantum error correction, which is, here's an example of something called the surface code. All of these circles over here are physical qubits, and this whole conglomeration represents one logical qubit. And the colored circles are measuring qubits that look for errors. And once I find them, then the way that I need to look at all of those measurements and decide where the error might have happened and try to correct it. A very active area of research, a lot of interesting things going on there. As we see that Kirk alluded to, we might need thousands of physical qubits in order to get a really high fidelity logical qubit. So we need scaling. There's all these compiler passes of how do you take even if you are happy building these, describing algorithms in this very low level sort of gate model, there's still a lot of work that has to be done to map what you think. You're thinking these are logical qubits. It's got to map those logical qubits to physical qubits, to gates that actually perform well on the machine, and so on. There's a lot of compiler issues, as well as debuggers, verification, benchmarking, a lot of software steps that need to be done here. And then scaling up is one of the big things we want to do. How do we, how many control signals do we need to get down to the chip? If the control is outside the dilution refrigerator, then how many wires do we need to go in? A lot of work going on there. Intel has a control chip that operates down at the cryogenic temperatures that tries to keep as much of that control locally as well. How do you put multiple chips together to scale up the number of qubits? A lot of interesting work from Rigetti and other people in that kind of space. So a lot of interesting things to do. And I will end there and say that these aren't just physical qubit engineering things. They're software engineering and systems engineering, compilers, application, languages, all that stuff is going to be enabling to get us to this point where the different developments that are happening in different companies and different groups around the world can work together and standardize and realize our quantum airliner at the end. So that's where I'll end, and I appreciate your time.
Well, let me first thank both Greg and Kirk for two excellent presentations, different angles. I only see one question in the chat, so I would encourage people to throw a few more. So let me start with the one I had before, then I see another one popped up. Well, this was from, sorry, let me just go back just a sec. From Bruce Allen Hecht, and this was a question, I guess, for both of you. Is there any proposed algorithm on quantum computers that would not be susceptible to Shor's algorithm? So he's referring to the integer prime factorization algorithm that quantum computers claim to be solvable in polynomial time. I don't know, anybody wants to take it?
So as far as determining an algorithm for a cryptography that assumes we have a quantum system capable of Shor's algorithm for the size of key that we are actually using, the NIST just came out with 4 proposed algorithmic standards. Of course, one of them was almost immediately broken on something with the power of a laptop. So yeah, there are proposals. There's now 3 remaining proposed post-quantum crypto algorithms from NIST, and they will continue to be evaluated. And where that will move is from proposal. For those of you familiar with FIPS, the Federal Information Processing Standards, that could become regulatory standards in a year or so. So there's definitely a lot of interest in regulated industry, because it's one thing for us to have the sort of the real concern on crypto is, are people harvesting data now? And some information, is only good for a couple of days. Some information is good in perpetuity, and it could be a hazard in perpetuity. And that's the kind of information that you're really concerned about. And so even if it takes us 20 years to get there, if the information is still valuable secret in 20 years, then you have to be concerned. And given the time that is estimated to make a switch over in like our public key cryptography and in international banking systems, that's the impetus right now for communities like NIST and FIPS, World Economic Forum. Lots of these global organizations are really driving hard on crypto now, not because they think that an RSA 256 is going to be cracked anytime soon, but given the longevity of hazard, it's part of they believe it's part of their fiduciary responsibility.
Anything to add, Greg? Or
well, I just want to, Kirk talked about maybe 20 years. I mean, you really need to appreciate how far away we are from being able to run Shor's algorithm on something that is of that size. We need at least 2 to 4 times the number of logical qubits as we have bits, and we need those logical qubits to do things like exponentiation and quantum Fourier transform over a long period of time, and so it's going to be a long time until the systems are able to do that.
My second question from Dmitry Bochko. He is interested to understand where you're going to get funding for starting high-risk quantum fundamental physics. Government, private, something else, or so does having a roadmap exclude interest in alternative quantum system research? I think this goes a little bit into, I think Kirk was talking about maybe the quantum winters coming from funding. I don't know,
So, I mean, just so people have an idea, we're talking about billions of dollars of investment. I think, if we go to Quantum Research is one of the boutique analyst firms, and yeah, they would put, the the U.S., EU, and several other allies at tens of billion, and perhaps even an equivalent amount in China. So there's real money flowing into this right now. So it's not a question of the money flowing right now. I think the question is, are we going to continue to see it? And also, again, this is mostly my personal positioning and grandstanding here. We have all benefited. The fact we can have this conversation over Zoom right now talks about the power of a academic, industrial, public, and private partnership to engineer absolutely phenomenal successes over a long period of time, if we have that model of pre-competitive leading to competitive environments. And I guess right now, it just seems like the quantum has kind of jumped directly into that, that driven by private capital in the venture fund, and we saw quite a bit of money flowing in there over the last 18 months, although now that SPACs may be a thing of the past. We don't know if we'll see that same equivalent for those who didn't get on that first round, as well as significant funding from national research. The question I have is it really, are we operating, given the model of success we've seen in the past, where we enjoy that robust international cooperative environment followed by the competitive environment? I think it's not clear right now that we'll have that. We have that model, and I think part of the challenge is twofold. One is that we've already described, which is the security question. Are we going to see some of these programs nationalized or limits placed on cooperation because of concerns that we just described in the cybersecurity realm, or because of the desire, either because a venture capitalist wants to get the maximum return, or a program is nationalized? Will we still see that the benefit of a collaborative international research environment continue to be fostered in quantum? And I guess that's everyone will have an opinion on that. I have a concern that we will continue to see that kind of cooperative model.
I think Greg, or good?
I guess the only other thing that I'll mention in terms of, it's not just the big guys that are the ones that you've heard about for the last few years. There are a lot of startups doing even hardware kinds of startups, and so just to go to the question, there still is a lot of good funding going at these different technologies to try to figure out what a good scaling model is, and maybe you use one technology for one part of your problem and another technology for another. There's the whole quantum internet thing. So there's a lot of opportunity, and it's not, I think, collapsing extremely quickly, but maybe a little quicker than Kirk might want to see.
Okay. I think you, Greg, your analogy there, well, being the son of an aerospace engineer, I love your analogy. And it's also, I mean, think about it. It was, from Kitty Hawk to landing on the moon was only 75 years. Now, the one thing it also immediately reminded me of is the fact that all of the Wright brothers IP ended up being thrown away almost immediately because their wing warping technology that was analogous to the natural function of bird wings proved to be untenable and was replaced by the Douglas brothers, normal actuated flight control surfaces. So I think, but I still think that there's a lot to be learned from these analogies and models, as long as we're careful. And again, for me, that's the interesting question. Where are we right now? Is I look at your gate diagrams and I thought, okay, yeah, because frankly, I started at HP in 89. In spring of 1989, I was trying to desperately pass my semiconductor physics class, and I did. And so I got to cash in that job offer that I got from HP over the spring break. But it turned out that while it was good to have that as a basis, the truth was, by the time I was thinking about circuit design, the tools were taking care of the lion's share of that burden. And directly to your point, I'd much rather have the computer scientists think in the abstract term, knowing that there's the nuances, but as far as all of that, we need, where's that equivalent of the EDA environment that allows someone to design, in system Verilog, and then have it go out to any of the available cutting edge, or even, some older fab technology, depending on what's the right thing. That's why we have computers to do that. So I think having those environments and really giving the computer scientists that I'll almost use the word luxury, that luxury to operate at the abstract level, and then figure out. Now the challenge is going to be is, again, I'll assert that we may never have one best, and that so that EDA analog is going to be a significant investment to see who's going to have that really optimizing compiler environment over all the modalities. And I guess for us also, I'll also draw the analogy. I was at a quantum conference and I said to the audience, who was all, I think I was the only traditional system engineer there. I said, what do you think about these numbers? 555, 741, 7400. And if you're like me and you grew up in the 80s, you remembered, well, that's the numbers of some of the most important individual integrated circuits were designed, all of which were essentially designed by hand with Ruby lift tape. And while that was fantastically effective, we eventually need to move beyond that. And I guess, again, I'll assert, I think that we're not at the integrated circuit level. We're not at the EDVAC general programmable level. I think we're still back at the RAMAC patch panel, but that doesn't mean that we can't actually find advantage in some of these if we can. You had the same diagram I had, which was understanding how we cross over from the cyber realm to the cyber physical realm to the quantum realm and back out. And can we talk about what that's going to take in terms of engineering at each scale, from 10 qubits to 10 million?
I think one difference in what's happening now, and we've looked back in the computing era, the open source thing is really different, and I think there's a larger emphasis in the quantum space of having things open source, the software at least, right? And there's a pretty good ecosystem around that. And I think those tools are being developed. Those EDA type tools are being worked on now.
Agreed. And that was another one of the venture investments that our Pathfinder did recently, was in investing in one of those quantum software companies, Classic, out of Israel, who is in that EDA like space. And I guess for me, that's why I was bullish on the venture team making the investment. It's like, yeah, this is what we'll need to get to eventually. So if to give your computer science students that luxury to think of the abstract circuit diagram and then have someone else shoulder the burden of understanding how to translate it down. And then I guess for me, where I would see, part of what we would have is understanding, again, from that cyber physical to the physical level, how do we actually engineer these systems to incorporate those QPUs, those quantum processing units, and understanding how we do that at each scale, knowing that. And I guess for me, especially when you showed like the error correcting, well, like that's a combination of manipulation and measurement in real time that's now being reacted. And what is or does that all have to happen within the dilution refrigerator or the vacuum chamber? Can we even tolerate the time to go in and out of these domains, or is it going to be something that is, again, much more small, focused, and bespoke? As you had your fascinating diagram of, okay, if we get a little bit more in fidelity, then we will go this way. If we get a little bit more on the complexity in which we can entangle, we'll head this direction. And frankly, think again, mapping all of that diagram over all the different modalities and then each of the individual approaches within a modality, that's a pretty complex diagram to chart over time.
I think we're approaching the end. I have one concluding question, since nobody else has, put in questions in the chat. I know you talked about, qubit being broken as a measurement, and we have like noisy qubits. And, if I look at the parallel in more of the traditional logic, we had broken measurements as well, but it kind of worked out, right? So, I mean, we had, gate length as sort of a proxy for process density, which we know is very imprecise, but, it doesn't measure metal pitch and whatever. We had gates, we had transistors. Do you see the community kind of staying with qubits, or do you see this moving into? I mean, people tend to like remember one or two numbers at most, right? In this world,
delay product. I want two things.
I mean, like again, process density and number of transistors kind of gets it right. So. So where do you see that going? I mean, is that it, qubits, and then we'll all argue about the definition, or is there something better out there?
Well, I think there'll be a number of measures, and I think that the quantum volume is something that Kirk mentioned. I mean, these are sort of efforts to capture that both quantity and quality of qubits, but also companies like IonQ are looking from an algorithm for how many computations can you do and things like that. I think the benchmarking activity is very strong and will continue to kind of set that pace. I don't think anybody's really happy with just saying the number of qubits. The number of qubits is a number that needs to go up, but it's not nobody claims that that's the story of how powerful a computer is. And so I think we'll see more nuanced measures of I don't know if we'll see one, but we'll see probably some application-oriented measures of what a particular system could do.
Yeah, great. I think that's I agree also that the raw qubit count. That's one of those. Yeah, it's almost a necessary. Also say, it's necessary. It is woefully insufficient if you actually want to do something. And one of the funny things is, again, talking to all the different companies, and especially when you get that first marketing pitch. That's why I included that kind of obfuscated roadmap. Is it's not sufficient to make a judgment. And unfortunately, when you have, it's like, oh, I use trapped ions because my coherence time is so long. It's like, so is the time for you to actually manipulate and run your qubit through one of these gates. Can you actually finish, even with your extended time? Is that sufficient to actually do the number of calculations we have to do? And if not, then we're talking about, because of all the things you point out with no clonum and no copying, it becomes so much more complicated. And I always think there's a Tolstoy line that says, all happy families are identical. All unhappy families are unique in their unhappiness. And I think for me, the analogy here is all logical qubits are identical. All real qubits are unique in their
unhappiness.
Unhappiness. And so that's where we are. And so it's going to be hard because there's so much pressure to demonstrate, that I'm making progress. I'm heading in the right direction. What my methodology is the one that is, and again, it seems like it's all a sort of a go for broke, as opposed to understanding that what we actually might need some superconducting qubits. We might need some trapped ion qubits. How do we actually begin to talk about these things in a way that is useful? And I do like your suggestion, Greg, that starting with an application, even if it's only one, that is meaningful, is the way that we will demonstrate. And perhaps again, back to some of the conversations I've had with people and people like Ray Bosley here at Labs is that might mean that we end up having a couple of them, and that's okay. Because if we can actually make progress on some of the most challenging calculations that we need to do efficiently as a species, then I'm willing to live with a couple different species of qubits.
All right, with that one, I think we reached the end of this session. I'd like to thank everybody in the audience for attending. The IEEE Santa Clara Valley section for facilitating this series of meeting, and particularly our two great speakers for a very entertaining and educational hour of quantum research. So thanks a lot, and stay tuned for follow-up meetings soon.
Thank you, Paolo. Thanks, everybody.
Thanks, everybody.
Thanks, Craig.
Thank you.